All right. So good afternoon, good evening, or good morning, depending on where you are. Thank you very much for joining the final presentation of the iCANX Scientist Award. This is of year 2022, the third part of the finalist presentation. And we have 6 presenters of today. And first, let me just briefly introduce and welcome my colleagues, the panelists, Ms. Kim, Zhang, Renhui Wang, and Paul White. And we will have 6 presentations, starting from Professor Chen Jun. And each of you will have 20 minutes. And we are aiming to finish on time at 10 p.m. So, without further ado, maybe I should present or let Professor Chen Jun giving the first presentation of tonight. The podium is yours.
Okay, thank you. So, hello, thank you everyone here. So, some of you is in the late night, some of you are in the early morning. I really appreciate your time, effort to put this great event together. So, I'm Jun Chen, Content Assistant Professor in Department of Bioengineering at UCLA, and today I would like to share you with your story entitled "Smart Textile for Personal Health Care." So first, let's look at this diagram. So why we need a personal health care? So this curve describes relationship between disease burden and the cost. So our current health care system is based on typical intervention. That's mean if you have symptoms, for example, if you feel headache, then you call a doctor, make an appointment, then you can drive. Then when the appointment arrives, then you drive a long distance to the clinic center, get some treatment. You can see this current healthcare system based on the disease management is high cost, low efficiency. Low efficiency means low doctor-patient efficiency. So I have been wondering about if we could perform early molecular detection. So what does that mean? The story could be like this. I have a body temperature sensor on my body, keep reporting my body temperature. If someday in the morning, if I wake up, I found my body temperature is a little bit abnormally high, compared with my historical data yesterday or 1 week ago, even 1 month ago, then I can report these abnormalities to the doctor over distance by just a phone call, a message, or email. Then they can give me an immediate tell. Maybe the headache will not come to me. So this concept of personal health care, you can say, is based on a disease prevention rather than disease management, and also it definitely has higher quality and low cost. So to realize this type of healthcare transformation, I think a key point that is we have to develop wearable biomedical devices, just like the wearable temperature sensor I showed you, I talked about just now. So we need those type of devices could be have wearing comfort and also has a low cost. Otherwise, people cannot afford those type of devices for healthcare. So how to develop those type of wearable biomedical devices with varying comfort and also low cost, actually the challenge in the field to realize this type of healthcare transformation. So Apple Watch is one of the famous one, actually is keep reporting our heart rate, but definitely has disadvantages. For example, is additional burden to wear and also very expensive. So textile actually is peaceful, indispensable component in our daily life, especially our human beings have a long history with textile. Textile itself has a number of advantages if you want to develop those into wearable biomedical devices. First, they have a wide range of materials choice, from synthetic materials to natural materials, and a lot of materials here actually are biocompatible, biodegradable, even bioabsorbable. But when we look at those materials, actually they are chemically inert, actually, and also they're not physically conductive. How can we develop those type of materials into wearable biomedical devices or wearable bioelectronics? Actually, there's challenge over there. So I noticed that actually human body has a lot of different type of biomechanical motions. So for example, when I talk to you now, actually my finger is bending and my heart is beating and actually I'm breathing. So I will be thinking about, can we use textiles to develop different type of textile product, which is convert those biomechanical activities into electricity. Then we have possibility of use this generate electricity for energy, sense, and therapeutic applications. So to realize this personal health concept I present just now. So 2 months ago, the editor-in-chief of Nature Electronics invited me to write a review paper to talk about smart textile for personal health care. So here I just want to share with you the first figure that is designed for that review paper. That's talking about timeline platform technology development of smart healthcare textiles. Especially my contribution majorly comes from those two platform technology. One is triple electricity, another is magnetoelasticity. So in today's talk, actually, I just want to use those two platform technology to show you how can we use those two platform technology to develop different textile products for biomonitoring, therapeutic, and energy applications. So the very first one is could be the sensing, that's the biomonitoring part. So the first story I want to share with you that we use those type of textiles for possible monitoring. So here is actually we use mimic the muscle fibers, use long-woven textiles to fabricate this kind of wearable bioelectronics. We show that when this piece of textile, like arteries, is able to convert the auto vibration into electricity, which is calculate number of peaks divided by time. We can see that actually our heart rate increased from 73 to 92 per minute after exercise. So those long-wave textile actually is neck compressibility actually is not that good. So far we also develop another piece fabric-based possible monitoring devices. You can see we are taking the silver-coated fabric as substrate on top of them create this kind of flower-shaped structure. So we are showing that while this type of device against the artery side is still able to convert the blood vessel compression expansion into electricity. So in the future, it's a well piece of textiles, then you can read out your possible profiles continuously and timely on your cell phone app. If you found some abnormality, you can report the data to doctor over distance immediately. Actually, for those type of wearable bioelectronics device relies on energy conversion, there's a big challenge that's motion artifacts. Because those type of devices not only convert auto vibration into electricity, they can also convert the finger bending or other motion artifact into electricity as well. So very recently, we also utilize machine learning algorithm to process those motion artifact induced electric signal. We show that even with body movement, so those piece of textiles can still monitor the heart rate very accurately, and also we compare with the commercialized cardiovascular monitors, so the results is actually similar to each other. So we also develop actually smart fabric, smart facial mask as well for respiration monitoring because COVID now become very popular and so, I mean, selectively popular. So basically, we develop some sensors on the facial marks. So this sensor actually is also very sensitive to the fluid dynamics between your mouth and also or your facial mask. This kind of cavities, we can monitor the fluid dynamic between this within cavities. So we show that we can use this facial masks to monitor different type of respiration behavior, normal breathing, deep breathing, or if you have a cough, or if you talk while the facial mask, or even you have a respiration failure. So actually, this facial mask can monitor different type of respiration behaviors with the accuracy as high as almost 100%. So as I said, for those type of textiles, actually respiration is actually a big challenge to this. But for the product I showed you previously, actually, they are not waterproof. So very recently, we developed a fundamental new working principle. What is the magnetoelastic effect in source system for energy and health care? So we show that this piece of wearable bioelectronics is intrinsic waterproof and actually is biocompatible. How does it work? I will use following slides to show you. So actually, what's magnetoelasticity? So actually, in 1865, the Italian scientist Yuerui, they found that actually in some metal alloy, when you apply mechanical pressure, you can see that. So the pressure up to 20 megapascal, you can see for some metal alloy, the magnetic flux density will decrease. So when you release the force, actually the magnetic flux density back to original state. But this phenomena actually can only observe in some metal alloy. So in 2021, actually our group at UCLA just discovered this effect in soft polymers. Actually, we just use some magnetic particles mixed with biocompatible polymers. We show that we apply mechanical pressure to such soft composite, so the magnetic flux density can also decrease, but the required applied pressure is reduced from 20 megapascal to 300 kilopascal. So those biomechanical pressure definitely is totally available from human body to deform such type of device for energy synthesis therapeutic applications. So here is one of the devices I show you. Basically, actually, we made this soft magnetic glass fibers to weave in textile configurations. Will show that when you, even with underwater situation, this device is able to convert a pulse wave into electricity. And we show that this type of device is biocompatible. So in the future, even you have heavy perspiration or even underwater situation, you can still read out a possible profile by wearing this type of magnetic glass sensors. So also show that this type of device is able to monitor respiration with heavy perspiration. So here, generate electricity when you normal breath, rapid breath, or coughing. So basically, we just analyze the general electricity. We can also monitor different type of respiration behaviors. So we also use this type of device to develop wearable human machine interfacing devices, while showing that even with heavy perspiration, so we can use those type of devices to control music player wirelessly. We also show that this type of device could develop into implantable forms. So because it is intrinsic waterproof and biocompatible, we show that when we attach the device in the heart of a rat, actually of a rat, you can see that they can generate electricity to show the destiny or systole of a heart beating. So actually, this could be implantable devices. So the second application scenario, that's therapeutics. For therapeutic, consider time limit here. I just want to share you with you one application scenarios. Assistive physical therapy. We show that actually 37.5 million Americans 18 older report trouble hearing, and actually 75% of them are unemployed because we don't have effective communication tools if we don't understand sign language. So here we just develop textiles gloves, which is able to convert the sense finger spelling, this kind of biomechanical motion into electricity, as I show you here. So while this type of gloves, you can see they can convert the American Sign Language finger spelling into electricity. So by using those electricity or the recognition patterns, we show that we can realize this type of wearable sentence-speech translation. So this work actually put out the top 10 science over 2020 and also covered by 200 media coverage in the world and also highlighted by Science, and also is made automatic top 100 among 3.4 million works published in 2020. So the last section, that's energy. So people may wonder why energy portion of smart textile for personal health care. Look at those future wearable biomedical devices. So they're very thin, they can be skin attached, but they definitely is power to drive them. So it's beyond the capability of traditional batteries because they are rigid and they're bulky, they radiate heat. During the discharging plateau will make you feel discomfort. So we think about, can we use textile to harness energy from human body and surroundings so sustainably drive those biomedical devices? So here's one of the solutions. Basically, we use a hybridized power textile, which is able to convert biomechanical motions into electricity by using this piece of triple electric textile. We can also use solar textile was made of desensitized solar cells, who are showing that they are able to convert solar radiation into electricity. So basically in a lab scale demonstration, we show that with this piece of textile, they are able to generate electricity directly towards your cell phone and drive smartwatch, and they certainly can drive some wearable bioelectronics in the future. So actually, using textile harvest energy not only limited to biomechanics, but also solar energy, but they can also convert heat biochemical into biomechanical, biochemical into electricity as well. So, but for this type of energy harvesting textile, they have a disadvantage because the energy in nature actually is not stable. For example, when you work in shadow of tree, there's no sunshine available, so the output will be largely reduced. So we still need to borrow the power from fiber batteries. So recently we developed solid-state zinc oxide fiber batteries. We show that this fiber battery actually is very stable. Even when you bend it or even you soak it in the water, they can have stable power supply. Actually, then we can also hybridize this kind of energy harvesting devices. For example, the fabric solar cell with the fabric batteries. So actually, with sunshine, we are showing that we can generate electricity stored in the fabric battery. At the discharge platinum fiber battery, we can always have stable electric output. No matter you're working in the shadow tree or working in the building, we always have stable power supply for wearable biometric devices. So actually, my vision to this kind of smart textile for personal health could be in the future, we can develop different type of test components for energy, sensor therapeutic applications. So we can integrate into a piece of garment. In the future, if you have certain type of disease, you just wear certain type of garment, then your disease will get treated. So then come to archaeology part of my talk today. Basically, I want to thank my wearable bioelectronics group at UCLA and also a number of collaborator contributors and also the funding agency. Thank you very much for your time and attention to my talk, although it's very short. Thank you for your. I'm looking forward to your questions, and I will certainly welcome you to UCLA in the future when if you have time. Thank you, everyone.
Thank you very much, Jun. Really appreciate. Now we have a few minutes for panels to ask questions.
Okay, maybe I go the first. Okay, Jun, very
sure,
nice
please.
talk. Yeah, I really enjoy this wearable electronics. And I have a question is for, you see that when you mounted all these kind of, different chips and different, target together with wires, right? Like the magnetic one. Yeah. So did you have any good solution to remove all this?
Yeah, this is a very good question. So certainly, because the wearable bioelectronics I developed here actually is the energy converter. So we need a lead well to read out the generated electrical signal, also voltage and electricity. So certainly, lead well actually is necessary here, especially when for the port, we have to connect our bioelectronic device with the circuitry port. But in the future, for other communication, for example, from the circuitry to the cell phone company, we can use Bluetooth or some RF or this type of technology to the wireless communication. But for the device, for the circuit part, definitely we need a needle well to connect the two components. Yeah.
Okay.
Yeah, I hope I answered your question. Yeah.
Yes, got it.
Yeah.
Yeah, I can go next. So I'm also working on wearable electronics and then not electronics, but fiber devices as well. But my question is, how do you control the reproducibility of your devices? So in the lab, when you fabricate the fiber-based devices or soft like micromagnets composites, like depending on the person and depending on the day, we can like produce a little bit of different performance like devices, right? So
yeah, it's possible.
And then if we want to go to the mass production, then I think we need some quantification of the variances. And do you have any solutions or any ideas about that?
Yeah, this is a very good question. So basically, to fabricate devices, we have different steps. So if we wanted to make the device standardize the fabrication of the device company, for each of us step, we have to come up with restrict this kind of fabrication steps or procedures. So for example, if you wanted to make this soft composite company, we have to use a machine to help you to mix the two together, and we have to fix the force used to mix the two, and also the frequency and the temperature and everything. So definitely, so far for our lab scale, this kind of research, so the device we certainly observe some variations of the performance between devices. But in the future, if you want to commercialize product, definitely we have to spend more time to, as I said, to standardize each of the steps to make sure every device come out from the product line is identical with each other. Yeah, but definitely still need time, effort to pay attention to each of the details. Yeah.
Okay, automation would be the answer. Thanks for
the
probably
automation definitely is a very good way to help the standardization of the fabrication. Yeah.
Okay, thank you.
Thank you for your question.
Thank you very much. Thank you. I think we are running out of time. And we hold the questions or comments until later. Next, we will be introducing our second speaker of today, Professor Yuerui from our Australian National University. Professor Liu, the podium is yours.
Yuerui, you mute. Yuerui, you mute.
Sorry for that. Sorry, let me share my screen one more time. Can you see my screen?
Yeah,
yes.
Very good.
Okay, thank you. Thank you very much. Hello, everyone. First of all, I would like to thank the organizing committee. It's a great honor to be here today. Today, I would like to talk about extraordinary light-matter interactions in 2D materials. Two-dimensional layer materials like graphene and transition metal dichalcogenide have become important building blocks for future electronic and photonic devices. Those layered materials show extraordinary interactions with light. Light-matter interactions can be divided into two categories, elastic and inelastic interactions. Based on the elastic light-matter interaction, we can fabricate lenses, gratings to control the propagation of light. Inelastic light-matter interaction can be used for optoelectronic devices that involve energy transfer. For example, photodetectors, solar cells, and so on. So here I would like to share with you two discoveries from my team: the creation of microlenses based on 2D materials, and the discovery of interlayer biextons from 2D heterostructures. So the first one is based on the elastic light-matter interaction, and the second one is based on the inelastic light-matter interaction. First, let's look at the microlenses. So microlenses have been widely used in our daily life, and future applications require next-generation miniaturized, high-speed, and focus-tunable microlenses. Electrically tunable microlenses are very promising for future integrated electronic system, but the challenge is the optical properties of the solid materials for lens making are very hard to be tuned by the electric signal. For example, the refractive index of silicon dioxide is robust, and the electrical tunability is less than 0.01%. Fortunately, those layered materials, their properties could be highly modulated by electric field. This is due to the unique van der Waals structure of the material. So this chart shows the side view of two monolayers. When we apply electric signal across the monolayers, this tiny gap can be slightly modulated by the electric field, leading to a large amount of the modulation on the optical properties of the layered material. This would allow us to fabricate electrically tunable optical elements based on those layered material. In my lab, based on the experimental measurements, we found that the high index material, for example, magnesium disulfide, can generate a giant optical path lens when light penetrates the material. This optical path lens could be at least 1 order of magnitude larger than that from the low index material, for example, graphene. So based on this, we fabricate a micro lens using the high index material, MS2. So we start with a MS2 plate with a thickness of 6.3 nanometers. Then a photon beam was used to kneel down the central part, atom by atom. And then a microlens will be generated. This chart shows the measured lens effect from the microlens. This was the first time to make a microlens with a thickness less than 10 nanometers. So those tiny lenses can enable many potential applications. One possible application is to make hundreds of microlenses in an array, mimicking the compound eyes of bees and other insects. I'm also currently leading a research project aiming to develop a small imaging device with the integration of those microlenses. This device will be small enough to be inserted into the blood vessels to provide high-speed and real-time images. This will help specialists to better understand the causes of heart attacks and how to prevent them. Next, I would like to talk about the interlayer extons and interlayer biextons in heterostructures. Interlayer extons are very promising for future low-energy electronics. Here, I would like to use exton transistor as an example.
Hi, Yuerui. You have some echo there, so can you turn off another, electronics or something? Yeah.
No, I didn't use another electronic. Sorry. Yeah. It's better now.
You get closer to your microphone, maybe. Yeah. So
yeah.
we really
It's
got
better now.
You try
now.
Better. Yeah.
Okay. Thank you. So in an exton transistor, two layers of semiconductors will be used. One layer contains electrons and the other holes. An electron and a hole will bind together to form an interlayer exton. Collections of extons will condensate into superfluid, which can flow without any resistance. This superfluid can carry electric currents in opposite direction in the top and bottom layer. In the past decades, scientists generated the interlayer extons in the double quantum wave device. But the challenge was those interlayer extons can only survive at a very low temperature, below 10 Kelvin, because their binding energies are very small, only a few millieV. So the monolayer semiconductors can host tightly bound extons with binding energies in the range of hundreds of millieV. So those extons can survive at room temperature. Also, people can stack two different types of monolayers together to form a heterostructure. From the heterostructure regime, people can observe the emission peaks from the intralayer extons that are still in the monolayers. Additionally, we can see a new peak in the low energy side from the heterostructure regime. This new peak was not shown in the monolayers. So this new peak was assigned to be from the interlayer extons from the heterostructure. This heterostructure has a type 2 band alignment. So when an electron hole pair is generated in this WSE2 layer, the electron can quickly transfer to the second layer and an interlayer exton will be formed. Comparing with those interlayer extons, those interlayer extons have shown a highly enhanced lifetime and a long range of interaction. Those will drive the system potentially into a superfluid. So there are two types of dipole interactions: the repulsive dipole-dipole interaction and the attractive exchange interaction. So when those two interlayer extons are far away from each other, then this repulsive dipole-dipole interaction will be dominant, and the total energy of the system will be positive. And this energy will show a blue shoot when those two extons are becoming closer to each other. When their distance is small enough, then the exchange effect will become dominant, and then this attractive interaction will bring down the total energy of the system from positive to the negative. At this point, then those two extons can bond together to form a robust interlayer exton, so interlayer biexton. So this biexton phase was predicted decades ago in theory, but it was never reported in experiment. There are two possible reasons. From this chart, you can see that this biaxial phase requires a very small interlayer distance d value here. This small d value is really hard to be realized in the quantum web devices. On the other hand, the 2D heterostructures can easily meet this requirement. In previous reports, the Doppler interactions in previous samples were highly reduced by the dielectric screening effect from the environment, which prevents the appearance of the interlayer biaxials. So here in our lab, we fabricate suspended heterostructures by transferring the samples across the micro holes that were patterned in the substrate. Here we use WS2 and WSE2 monolayers to form a heterostructure with the type 2 meta-alignment. So from the PL spectrum, we can clearly see the emission peak from the interlayer extons, only from the suspended area at room temperature, but not from the supported sample area. So when we cool down the sample, we can still see the interlayer exton emission from the supported area, but the normalized intensity was much lower than that from the freestanding part. This suggests that the reduced dielectric screening in this freestanding sample part can highly enhance the formation efficiency of the interlayer extons. This is very important because this will provide a new degree of freedom and will allow us to study those samples with a very low emission intensity of the interlayer extons. For example, those heterostructures with a large twist angle. So a 2D heterostructure with a large twist angle is very promising for the study of the interlayer of the Doppler interaction, because the lifetime of the interlayer extons will be highly enhanced, and we can easily generate a high level of the exon density using a CW laser. So here, this is a trade-off. For those samples, the emission intensity of those interlayer extons will be very small, and it was too low to be detected in previous experiments. So here, we fabricate a suspended 2D heterostructure with a large twist angle of 51 degrees. From the suspended area, we observed a very strong clear emission peak from the interlayer extons, X1 and X2. When we increase the exon density by increasing the pumping power, we can clearly see that a blue shift. This blue shift was caused by the repulsive dipole-dipole interaction, which was consistent with previous reports. So the interesting thing here, the high energy peak IX2 showed a small blue shift followed by a large red shift here. So this suggests that the Doppler interaction showed a transition from repulsive to attractive. This type of attractive interaction was never reported in a 2D heterostructure. And then the further study confirms that this red shift was caused by the formation of the interlayer biexton phase. This fundamental discovery can help scientists to better understand and engineer the dynamics of the Doppler interaction, which can potentially drive the system into a superfluid. Now, what does this mean to us? The moving speed of extons in traditional semiconductors is limited, similar to a car traveling in a city with full of traffic. The superfluid can be visualized as a superhighway that allows extons to travel at a very high speed with a very small, very low energy consumption. So this can potentially enable next generation low power, super fast information technologies based on extons. Finally, I would like to summarize my talk. So I introduced the micro lenses based on 2D materials and the discovery of interlayer by extons. So I believe we can develop more interesting applications based on by harnessing the strong light matter interactions in 2D materials. Finally, I would like to acknowledge my collaborators, team members, and funding agencies. Thank you very much for your attention.
Thank you very much, Professor Lu. Yeah, session is open for questions.
Hi. Hey, Yuerui. I'm going to start by asking a couple of questions.
Sure.
Regarding the exciton transistor and the exciton highway vision you have shared, it sounds quite exciting. One question I have is, given that exciton is charge neutral, so is biexciton, how do we use that to carry information or electrical charge?
Okay,
Because they are not trions, but trion is follow different statistics, right? One is fermion, one is boson, so it doesn't follow the same statistics. So yeah,
Sure.
how do we mitigate that?
So sure, that's a very good question. So for example, as I mentioned in the video, so for example, for this exciton transistor, you can see here, so the top layer carries the electrons, and the bottom layer carries the holes. So when the exciton flow from the left to the right side, the electric current on the top side is in the opposite with the bottom side. So you can still generate the current flow from this input, and then it flow out from the output. So this is one example to show we can use an exciton to actually to build electrical devices, even though exciton is fundamentally neutral. Yeah. And then also exciton can be used into exciton circuits. For example, we can use the electric gate to control the on and off for exciton transport in the circuit. And then this can also help us to build a very fast interconnect for future of electronic devices. So this kind of exciton circuit can fit in the interface between the photonic and the electronic devices.
Okay, can you just go back 2 slides?
Sure.
This is it. Yeah, so actually, sorry, slide 15, please. I was just going back 1 slide.
Yeah.
Next, slide 15. Yeah, so on the figure to the right, what are you using to change exciton density? Are you using?
We
what's the
increase the pumping power? So here, so this is the equation. So we can increase the pumping power to increase the density of the exciton density. So for example, here we measure a power dependent optical measurements. Yeah. So at high power, we can generate higher exciton density. At low power, we can generate a low exciton density.
I see. And one final question from me. What's unique about this 51 twist angle? Doesn't seem to be a particular Marie pattern, or I don't see mini flat bands showing up in your data. Why is that you're picking 51 degree?
Okay, that's a very good question. Due to time limitation, I didn't talk about all the details. So 51 degree actually is H-type stacking. It's 9 degree away from 60 degree. So for this H-type stacking, we can see here, actually the IX1 in our experiment, we've confirmed that this IX1 peak is coming from the Mori trapped interlay exciton, and this IX2 is coming from the free interlay exciton. Yeah. So for X1, because they are trapped in the Mori traps, so those kind of Mori traps can potentially prevent this kind of Doppler interaction. So that's why for X1 we didn't see a very clear this kind of attractive interaction. But for the free interlay exitons, they can interact with each other freely, and then there are more chance for them to collide with each other. So that's why we were able to see this kind of attractive interaction. So in our case, we didn't see this kind of flat band because the twist angle is more far away from 3 degree. Actually, we fabricated a few more samples, but 51 degree is not intentionally chosen. We just need to increase the twist angle a little bit far away from 0 or 60 degree.
Okay, thanks.
Yeah, no problem.
Thank you. Thank you. Do we have further questions from the panel?
I can make one quickly. So it might be a little bit general question. So I was wondering how the lattice mismatch between the 2D materials and then the substrate affect the optical performances.
You mean the interface between the 2D material and the substrate, right?
Yes.
Yes, that's a very good question. So actually, due to time limitation, I didn't mention that we in our experiment, we can exclude this kind of interfacial state from the sample. Obviously, when we put the 2D materials on the silicon dioxide substrate, the interfacial state can affect the optical properties on the substrate. So previously, people always need to use HBN, hexagon boron nitride, to passivate those 2D materials. But the problem for that is the HBN can also provide a very strong dielectric screening to the 2D layers. And so that can also further prevent this kind of Doppler interaction. So in our case, we made this freestanding sample. So we can both, we can remove the dielectric screening at the same time, we can minimize the interfacial states to minimize the influence from the substrate. Yeah.
Okay, thank you very much.
No problem. Thank you.
Thank you. Since we have still a little bit more time, maybe I can just ask you a quick question. What do you see as a major barrier for the vision of extern transistors or extern, I'll say, information processing to come true?
Okay, great. That very nice question. So first of all, I think those 2D materials they are better because the binding energies of extern could be much higher than those those 3-5 semiconductors. So they can potentially survive at high temperature. Now the current barrier is how to realize this kind of superfluidity at a higher temperature. And currently, I believe we can potentially realize this kind of superfluidity above this 78 Kelvin. That shouldn't be a problem. But how to push this temperature further, make it close to room temperature, that could be still challenging at this moment. But eventually, I hope we can have ways to overcome those challenges and we can make this happen for future low energy electronics. Thank you.
Thank you very much, Professor Lu. Really appreciate your questions and answering session. Due to the time limits, we are sorry to move on, and let me take the opportunity to thank you and introduce the next speaker, Professor SHASTRI Bhavin from Queen's University.
Thank you very much. Let me share my screen and hopefully you can hear me loud and clear and you can also see my screen okay?
Yes,
wonderful.
Thank you very much. Really appreciate it.
Thank you. Okay, I'll start. So thank you very much, first of all, for having me here. Today I'll be talking about how we're implementing neural networks that are inspired by the brain on photonic hardware. On the left here, you see this chip here where it's enabled by silicon photonics. This is fully powered by light. And the idea is to enable new applications in artificial intelligence and also potentially it can be used in quantum information processing. Now, a lot of work started in this area by Professor Paul Prusnell, in whose lab I was as a postdoc. And I would like to acknowledge him and also my other collaborators have contributed to this work, including the fabrication support that we end up getting. And of course, I would not be here without my students. So this really speaks to them all doing all this brilliant work. And I'm here just as a spokesperson for all the work that they are doing. I'm very grateful for this opportunity. So we know artificial intelligence is all around us, from natural language processing to autonomous vehicles to drug discovery. And in a lot of cases, machines have, approached or even exceeded human level accuracy. And AI by itself is not a new field. It's been around for a very, very long time, but it is actually enabled by what are called neural networks or artificial neural networks. And here's a schematic of an artificial neural network. where you have layers of neurons, which I'll explain on the next couple of slides, that are interconnected with the next set of neurons. And what happens is that the data in this type of networks is input as a vector, and it gets processed by multiplying this vector with a matrix which is this interconnection of neurons. And each layer does something very unique. For example, this first edge, the first layer here could be identifying edges. For example, if you put a human face here, the next edge, a combination of edges, you can then identify more complex features and a combination of features. And then you can say with some probability who this person was, in this case, George. Now, as you can see, you need to do a lot of this vector matrix multiplications, but you also need to load a lot of this data from to and out from memory. And this creates a lot of compute power challenges. So here on the y-axis, we have plotted the compute power required to train the AI systems on a log scale. And what we see is that for many years, the compute power required to train AI systems was doubling every 24 months or so. And this was okay because computers were able to keep up because of Moore's law. But over the last few years, we have seen that this compute power is doubling every 2 months. And so even if you had, Moore's law was able to keep up, it's very difficult to start matching this type of compute power. And therefore, for a lot of AI systems, you need thousands of CPUs and hundreds of GPUs working in unison to implement AI algorithms. Now, this comes at a huge cost of course, with large training models. You're paying a huge energy cost. You have all this heat that is being generated by all these computers. You need to cool it down. And for that, of course, results into a lot of carbon emissions in the environment. And just to kind of give you an idea, to train a single AI system, you can spend more carbon footprint than actually taking a round-trip flight between San Francisco and New York City. On the other hand, we talked about the energy, but there's also speed consideration. Today, these neural networks are implemented in software on digital hardware, and this is limited to a few hertz to kilohertz timescales, and therefore the applications are in sort of like object or speech recognition. There's been move towards going to what's called neuromorphic hardware, where you try to implement this neural networks in hardware using the physics of the devices to emulate the biology. This was work done by Misha Mahawal many years ago, where she talked about basically the reason for doing this is to do real-time processing, consuming as little energy as possible and fabricating as many neurons as you can on a single chip. So a lot of work has been done in this area by companies like IBM and Intel and HP using analog electronics. The challenge here is interconnects. So as soon as you have a neuron and you need to connect many wires to it, what we call fan-in or fan-out, you get limited by electromagnetic interference and capacitive loading, also topological constraints that really limit the bandwidth. So you have to have a trade-off between how complex you want to make your systems or how fast you want to go. And therefore, these systems are really limited to a few kilohertz or megahertz timescales. What I'm very interested in is what we call neuromorphic photonics, where we are trying to implement these neural networks on photonic hardware. And this can potentially open up a whole new class of applications from optimizations to signal processing to even, and also real-time quantum tomography, essentially opening up the picosecond time scale and processing on a gigahertz bandwidth. So these are applications that can be enabled, which will be very hard to do so in electronics. If you want more information on sort of this on the background, you can check out our paper that I've highlighted at the bottom. So digging deeper, this neural network, if I zoom into one of these neurons, it's essentially doing a very simple operation. You're basically getting this input vector here, X, and you're doing element-wise by element-wise weighting. So this is called essentially a dot product of two vectors. So that's the linear part. And then you have the nonlinear part where you're essentially applying a nonlinear activation function on this received sum, and you're making this decision whether that signal goes through or not based on some threshold. So we implement this in photonic hardware, in silicon photonics, where we take this vector X and modulate it on different wavelengths of light or different frequencies of light. Now we can multiplex all these frequencies of light on a single waveguide. Now we can use what are called these tunable filters called ring resonators. So you can think of this as just as tuning knobs of a radio, where you can tune between different frequencies or different stations. This is exactly the same, but with different frequencies of light, where you can tune between different frequencies or wavelengths of light, and you can control the amount of light coming out of these waveguides. So you can do the weighting that way, and then you use this photodetectors to sum up all the wavelengths, essentially giving you the dot product of the two vectors. From this electrical energy, you can convert back into the optical domain using a modulator, and you can extract and you can exploit the nonlinearity with this modulators for the nonlinear activation. So we have implemented this fully on a silicon photonics platform. We have shown that you can actually do this dot product of two vectors. Here is sort of on the right-hand side, top right-hand side, you can see the expected versus the measured results. And you get, really good precisions for this type of systems. And this paper was just published a few weeks ago. For the nonlinear side, we take a piece of silicon and dope it with two types of material, like say P-type and N-type, and that creates a depletion region. And so now you can modulate, if you can modulate the width of this depletion region, you can essentially change the number of free carriers that you have. And once you do that, to the first order in silicon, you can change the refractive index and also the absorption in this material. So we fabricated such a device, and by biasing this at different operating points, you can essentially get different types of activation functions or nonlinear characteristics which can be used in different types of neural networks. So putting everything together, you can get both the linear part and nonlinear part monolithically integrated on the same platform. And we were the first ones to actually demonstrate this. The efficiencies that we see today is around 500 femtojoules for a vector operation or a MAC. And you can get this down to even 1.1 femtojoules per MAC by carefully constructing the capacitance of these modulators. And of course, you can operate in tens of gigahertz speeds. So in my lab, we have come up with these tools where you can make this large-scale photonic integrated circuits from doing all the layouts, sending them to foundries, and this is done purely on standard foundries. We get the chips back, we package them with wire bonding, the PCBs, and we program them with machine learning libraries to look at all these new applications. So more details are found in our paper that was published last year at the bottom here. So one of the applications that we looked into is in fiber communications. The reason we're able to speak today right now is because of optical fibers that's enabling this communication. So this can be really long pieces of fibers for almost 10,000 kilometers, and you have all these non-linearities that you need to compensate for, like four-wave mixing, cell phase modulation, and others. The way it's done today, that optical analog signal is converted into some digital electronic signal using an analog to digital converter, and then you do this DSP. And this is what's really limiting the speeds of this type of systems. And so our proposition was that if your signal's already in the optical domain, they're already in the analog domain, we can use our optical neural networks to process them directly. And what we were able to show, and this was surprising for us, that we can actually get better performance than the DSP, than what DSP chips can do. So more details of this work are given in this paper. Another application is in wireless processing. For example, if the two of us are speaking and there's a lot of music and a lot of chatter going on in the background, our brains are able to isolate signals and we can still talk to one another. And so we're able to extract these independent components. And so this is called blind source separation. And the way this works is essentially, if you have many, many independent components and you add them together, you get a Gaussian distribution. And so the idea is that if you can make this receive samples as non-Gaussian as possible, then you can extract these independent components. This can be done by what's called independent component analysis, where you essentially are maximizing what's called the kurtosis, which is a fourth order statistics. And this can have applications in radio astronomy. So for example, if you were to use pure electronics to do this, and you wanted to span the whole spectrum of almost 20 gigahertz from all the way from, say, civil and military applications to Wi-Fi to radio astronomy, the bandwidth of electronics is quite limited to a few kilohertz, a few megahertz, and you would need M such receivers with N such antennas. And for each one, you need analog to digital converter before you can go to the DSP. So your power scales here quadratically. With our photonics, what we can show is with a single photonic chip, we have this bandwidth that can cover the whole RF spectrum, 20 gigahertz. And here the power scales here linearly because you can do all this processing in the analog domain and then just use a single analog to digital converter. So we were able to show this experimentally just very recently and separate this signals, with different modulation formats over 20 gigahertz with very good signal to noise ratios. So this paper has just been accepted, but you can find the version on arXiv. So another last application that I'll talk about is, this are all classical applications, but people are also very interested in quantum information processing. And what we know is that photonics is a very good platform for doing quantum information processing. For example, you can use this meshes of what's called a Mach-Zehnder interferometers, as it's crisscrossing waveguides, and you can essentially implement any type of quantum gates with this. Now, I'm not a quantum computing person, but this is an interesting application to look at. So this is an example of what's called a Bell state analyzer, where you have this maximally entangled states here, and you might want to project them into some type of computational basis, maybe for applications in quantum communications, which I'll talk about. The point here is that even if optics can be used, linear optics can be used to implement any type of gates, the maximum fidelity that you can get, maximum success rate you can get is limited to around 50%. Even with the best fabrication and everything, this theoretically, that's what the limit is for this Bell state analyzer. And if you had noise or fabrication imperfections, this probability, of course, goes down. Now, this becomes even more significant if you're making a quantum communication network, for example. This purple dots here are quantum repeaters. They generate some type of entangled states, and then they send them to this Bell state analyzers to do this entanglement swapping and then create this long communication link. You need many Bell state analyzers, and if you're starting off with a probability of 50%, you can see that this drops off perceptibly, if you have, say, 10 Bell state analyzers. So what people have investigated is that, look, if I can implement some type of nonlinearities, not purely linear optics, if I put some type of nonlinearities, then theoretically I could get 100% fidelity. And so we started investigating how that can potentially be possible. So here you have a mesh of this linear Mach-Zehnder interferometers, and we're looking at the single photon nonlinearities implemented with this quantum emitters. One of my collaborators is fabricating this. And with different types of noise and different types of fabrication variations, we were able to show that you can, in fact, get almost near deterministic quantum information processing, even with weak nonlinearities, by compensating with the number of layers that you can have in this type of network. So you can essentially learn to account for this fabrication imperfections and train essentially in situ. So we think that these are some interesting applications that one can look at. Just to start wrapping up, there are a number of applications that we have looked into, for example, in solving nonlinear optimization problems, where we want to do some type of predictive control in autonomous vehicles. We had a few papers that we published in this area, also in doing partial differential equation solving or ODE solving with our neural networks. We have looked into that. Of course, I've talked about doing fast vector matrix multiplications in fiber communications and also wireless communications. Another area that we are very much working on is with people at CERN, at the Large Hadron Collider. We're trying to use our neural networks to classify high energy particles, and also, as I mentioned, in quantum information processing. More details are given in this paper here. So in my last 1 minute, I'll just give my perspective. We have come a very long way from people when they were starting to use analog photonics with scalable computing models, work done by Dimitri Saltis in the 1980s. Some pioneering work on optical neural networks. This was all free space optics. And then in the mid-2010s, we saw the rise of silicon industry with scalable compute models, so neuromorphic electronics, but this is limited by bandwidth. And now with programmable photonics, combining everything together, we get this field of neuromorphic photonics, which has enabled all these applications that I just talked about. So our idea, and I'll just wrap up in the next 10 seconds, is that we're looking at all the way from doing device level work, integrating frequency foam lasers with photonic wire bonding, to making circuits and doing monolithic integration of our CMOS and also memory. So thank you very much. This is my vision, and I'm happy to take questions.
Thank you. Really appreciate it. So the session is open to questions. Please unmute yourself, our panel members. If you have questions.
Hi, Max, you go first.
Okay, yeah, thanks for the talk. I'll start with a quick question. When we do on-chip photonics for classic information processing, the attenuation of signals through those on-chip waveguides could be quite challenging. And if we talk about quantum information processing, then the defacing and loss of coherence would be also very challenging for these on-chip systems. So what's your vision in mitigating these challenges?
So that's a very nice question. So typically what we are concerned with when we're making this large scale photonic integrated circuits is exactly what you said. We are concerned about loss. And there are a number of ways that we overcome this. Number one is where what we are fortunate in our systems is to apply nonlinearities. And by applying this nonlinearities, essentially, we are using this electro-optic nonlinearities in our silicon photonic networks. So here, for example, as I talked about here, we are converting this with this modulators, for example, you are having this photodetectors that drive this modulator. So it's not purely optical, it's an optoelectronic type of system. And we then show that this can actually then drive the next stage. So this is one way where you do signal regeneration, and this is what helps to overcome this challenge of cascadability. And the same thing there with the quantum part, where we are looking at the single site nonlinearities. We have this quantum dots, which help us to regenerate the signal. So this is why going from linear optics to having some nonlinearities can actually help.
So basically, we are trading more power consumption for this kind of signal fidelity, right? Because every time we regenerate the signal, we have to put in some energy.
That's right. So we have some optical pump here where you need to provide some energy to the system. But the idea is that if you can make this modulators really efficient, this is essentially limited by the junction capacitance. You can use, for example, people have shown you can use a few hundreds of attujoules per bit to regenerate the bit. So you're right. Yeah, you need to provide some extra energy to be able to do that.
Okay, thanks.
Okay, I can go next. So I have two questions. So the first thing is, you actually provided some of the challenges that you have to go, and then thanks for sharing the vision and the roadmap. I love the last page of your roadmap. And then my question is, what are the materials perspective, like materials aspect challenges in identifying that they're realizing this on-chip neuromorphic systems? Like there could be so many, because like between dissimilar materials, the adhesion problems and the material dissimilarities, everything. But from your side, what are the biggest materials aspects challenges?
So this is a very nice question again. The challenges where we are trying to really advance the technology, but also do some type of fundamental science. And we are there's a trade-off, because we want to be able to create this large scale system. So we have to go to foundries to be able to do that, but they're only working with silicon. And so any post-processing we have to do in our labs. So for example, graphene is a very good material where, for example, if we wanted to go to low temperatures, for example, these people are looking at low temperature neural networks, integrating graphene with silicon, also polymers. Polymer-based devices with silicon, because you can get very high modulation efficiencies and very high speeds. So these are definite challenges, but the problem is right now is that these are not standard silicon photonic processes. So we have to do them in-house. There's also this integration. There's also this challenge of integrating different materials, like, for example, our lasers on a 3.5 platform, even our quantum dots are on 3.5 platform, and we need to integrate to them with silicon. And so we are coming up with technologies, for example, creating this 3D photonic wire bonds to integrate them together. And similarly, when we want to integrate things like phase change materials, this is also being done. Everything is done on as a post fabrication step. So there are lots of challenges like that. We think that we need new materials to be able to get better efficiencies and better performance. But the challenge is that at the same time scaling these platforms up. Yeah.
Oh, thank you very much. So if I may, I have one more question. So yeah, so you mentioned that the machine learning can accelerate the whole computing time, and I agree with that. But could you do you think it would be possible to provide any quantitative values, like how many percentages or how fast that would be?
Yes, absolutely. Let me just quickly show a backup slide here that that will help. There we go. Yeah, so if you look at today, just with today's hardware, we look at, say, the Google TPUs, which has been actually used for a lot of this machine learning applications. Those things work at around 150 gigamax, or giga operations per second, normalized per unit area. And with this photonic cores, that I've presented, you can go, with today's technology, you can go up to 15 teramax per second. So this is almost a speed up from giga to tera. And this is, of course, normalized per unit area because our photonic devices are much larger than the electronic components. So this kind of gives you a scale more quantitatively. You can plot this where you can show where the digital electronics is and where photonics can potentially go. But we have to also keep track that there's also analog electronics as well, which can potentially get very good efficiency. So these are the type of roadmaps that people in optics typically use in terms of the energy and also the speed. Yeah.
Much.
Thank you so much.
Thank you. I'm instructed that we will be taking 5 minutes break between the third talk and the fourth talk. So this is our break time, and thank you all for your participation. We'll be back in 5 minutes.
Thank you.
不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的人旁。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的人旁，不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的人旁，不再 再被曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。
All right, so thank you very much for your attention. Welcome back. And in our coming sessions, we will have 3 speakers. So the first one will be presented by Professor Felice TORRISI from Imperial College London. Professor TORRISI, the podium is yours.
Right, thank you very much, first of all, for selecting me for this presentation. It's really an honor to present at iCANX. And today I'm going to really give a short overview of the work that we did on the electronic transport of printed two-dimensional materials with specific applications to wearable electronics. So essentially, the wearables, as we know them, are defined as a kind of mix of interconnections, sensors, devices or transistors, light-emitting devices that are essentially still rigid. So neither of these is breathable or stretchable. So what if we could actually make devices that indeed fully integrated with textiles, for example? So devices that really have devices that are compatible, for example, with textiles, with fibers, or can have an intimate contact with skin. So for example, they can give us information of our body or for example, direct us in specific situation. So definitely to do that, we need new materials. We need to go beyond the materials that are currently used in the wearables as we know them that are more similar to bracelets. So we need maybe materials that are more stretchable. They're definitely low power, because you want to have something that can be directly powered locally. They need to be conformable to skin and ideally breathable, which is an extremely important point that sometimes gets neglected. And in some cases, easy to integrate with clothes and also washable. So textile is definitely an ideal material. It ticks all the boxes that I've talked about. But however, textile per se is passive. So we need to definitely make it more functional. And so my research has been actually in exploring whether graphene properties, like for example, the transparency of these materials, the conductivity of these materials, they can be tuned down to very few ohms per square, and particularly the mechanical properties, so stretchability and conformability. And more recently, there's been a lot of work on graphene and 2D materials biocompatibility, also due to the pandemics, actually have demonstrated that these materials could be extremely promising for wearable applications. So the graphene preparation has been heavily explored in the past. And actually, we contributed quite a lot to that. So normally you can start from, for example, from graphite or layered materials. You can use different sorts of shear forces to exfoliate graphite, ultrasonic exfoliation, shear mixing, or microfluidization, for example, to get a so-called graphene ink. And this has actually had a lot of improvements over the past. So it's possible to start with graphite, for example, and after a few exfoliation cycles, you can actually reduce your graphite to really thin, large platelets that have electrically actually an enormous advantage when it's exfoliated. I mean, it has been demonstrated that if you go from graphite to graphene, it's possible to reduce the sheet resistance of printed films dramatically from, for example, decades of ohms per square to really below 1 ohm per square. This is also because you can reduce the overall thickness of your material. So you can achieve conductivities that are state of the art of carbon-based materials at the moment. The big advantage of layered materials is that you don't have just graphite. you can rely on boron nitride, metal dichalcogenides, for example, max phases, to really create a platform of layered materials. For example, transition metal dichalcogenides offer modulation on band gap, so you can make, for example, semiconductors. And more recently, MaxScenes have actually shown that you can exfoliate, for example, max phases by etching the group 3, group 4 elements, creating very thin platelets, for example, of generally MX components. So, for example, titanium carbides, niobium carbide, or molybdenum carbide. So this definitely enabled us to create a platform of printable inks. So you can have MaxScene inks, you can have graphene inks, and you can have, for example, transition metal dichalcogenide inks with very, very similar properties. Large flakes in the order of 100 nanometers, even 1 micron, and very thin in thicknesses. So the big question initially we wanted to tackle was actually, what is the transport like in these materials? Because if you want to make electronic devices, you need to know what's the transport. So what we did, we actually inkjet printed these 3 materials, and we created bottom gate and top gate transistor connected with 6 electrodes, and also a different configuration connected with ionic liquid gating. And this really enabled us to essentially get out the electrical properties of these materials. Here you can see, for example, a graphene ink that can be inkjet printed nicely from a standard Epson cartridge, generating single droplets. That's what you want when you want to control the concentration of your material. And then after we printed it, we characterized the conductivity as a function of temperature. You can clearly see that the transport is very, very different. So MaxScene, titanium carbide, MaxScenes are definitely metallic. So they have a clearly metallic behavior across a very large range of temperatures. Graphene shows a more semi-metallic behavior. So the modulation in conductivity is not very broad, but it's still actually decent to show some sort of modulation that we normally see in field effect as well. And then MOS2 is clearly a semiconducting material with an insulating behavior at low temperature. And this is also demonstrated by looking at the behavior of the graphene ink when it's modulated with a gate voltage. Here we are sweeping across a very large voltage range, and we can clearly see that it's possible to gently modulate the graphene as it's known, and the modulation also varies with the temperature. So this is typical with interflake hopping, which is dominant in graphene inkjet printed devices. With MaxScene devices instead, you see that the modulation of conductivity is almost 0. So essentially it's a clear metal. And even if you apply gate voltage, essentially the conductivity doesn't change too much, and it doesn't vary with temperature. So this is clear of a typical charge transport over extended states. Essentially it's a metal, and we could be using it as a very good electrode. MOS2 ink instead is a typical semiconductor. As you can see here, we can switch on and off the conductivity at different temperatures. And the interesting thing is that we can actually switch from an insulating behavior to a conducting behavior, which is mainly given by intraflake hopping. This is a more fundamental study that we did, and we worked out actually a pretty decent mobility of 10 to the minus 1 centimeter square volt per second with an on-off ratio slightly less than 100. And then there is this interesting gate-induced crossover, which I don't have really had time to discuss about, but it's more fundamental. And this is switching between band-like transport and actually transport over extended states. Anyway, understanding the transport enables us to make very good transistor. So we could make very good inkjet printed transistors with MOS2. And this also enabled us to create integrated circuits. So go from a single device to actually get integrated circuits. In this case, we have a typical NMOS logic, because MOS2 is a typical NMOS device. But you can also couple MOS2, for example, with organic devices to make complementary logic, as we did. Now, the big question is, if you want to use these materials for wearables, can you actually make it printable? Well, to do that, we need to enable 2D material inks that are washable, flexible, and also they can be fully integrated with textiles. So, well, the first thing you can do is you can take these inks, change a bit their formulation, then, for example, screen print them. And, a lot of people can do this. You can make reliable electrodes with a very good conductivity, but we wanted to go beyond that. We want to make active devices. So we actually focused on creating wearable field effect transistors on textiles. In this case, we have devices that are fully made of 2D materials inks. In this case, we have a graphene channel with a boron nitride dielectric materials, and then gates, source, and drain that are P.PSS. And in this case, we can nicely modulate our transistor. Typical behavior of graphene modulation, of course, is not very high because it's a semi-metal, as I explained you, but we find a fantastic mobility compared, for example, to other printed devices, around 100 centimeters square volt per second. And another very important point that I want to stress, which is typical for wearable devices, is the power consumption. We have less than 10 microwatts, which is compatible, for example, with integrated devices. Of course, we don't like single devices. We want to demonstrate proper technologies here. So what we did, we started creating, for example, integrated circuits on textiles, no rigid devices here. So this is an inverted, fully printed on textile, and this is an OR gate that shows the typical output waveform of an OR gate with a truth table of 0, 0, 0, 1, 1, 0, 1, 1, as you can see here, and the device nicely responds with 0, 0, 0, 1, 1, 1. So we demonstrate for all textiles inverters and also all textiles reprogrammable memories and logic gates. So then this enabled us to move towards something which is crucial in wearables, which is washing. So this device can be washable more than 20 times. And the way we did it, actually, we took our transistor arrays, we put it in a washing machine using a standard ISO process. And in this case, we washed it for 30 minutes at 60 degrees with a typical washing powder. What we see is that the mobility doesn't really change in these devices. There is actually a slight increase in hole mobility, which we couldn't really explain. You know, it might be some water remaining in the dielectric, but essentially the mobility stays the same. And also this device continues working and modulating nicely after different bending cycles and different washing cycles, as you can see here. So what we can use these devices for, everybody knows that graphene is not really good for digital electronics. So one application is actually graphene biosensing, and graphene is actually very compatible with already existing tissues. For example, neuronal cells grow very, very nicely on graphene. So what we started doing is creating an array of graphene biosensors on cotton fabric with a specific conjugated pad that allows to absorb the analyte and then carry it towards the graphene biosensors. And the idea is to use our graphene field effect transistors in a liquid electrolyte configuration. So it's an electrolyte gated transistor for wearable biosensor targeting specific analytes. So the device I'm talking about looks like this. Essentially, we have a textile substrate, source and drain electrodes, the graphene channel, and then gate electrode with a liquid electrolyte, and then a reference electrode. And in this case, our device can nicely explode the Dirac point of graphene. So essentially, the point of maximum resistivity of this device that actually shifts, as you can clearly see here, with the pH. So this can be linearly controlled to actually draw down a very nice linear curve of the Dirac point as function of pH. So this can essentially be a controllable way to find out the value of pH over a very, very broad range. And then, of course, we can use this to maximize our resolution because, of course, the shifting of the Dirac point is very, very sensible in a graphene field effect transistor. It's a very sharp change of the resistivity, achieving a resolution which is actually beyond state of the art in this case, in even in clinical applications, of 0.04 pH units, with a response time of less than 10 seconds and a very, very broad pH range. And here you can see actually that the device is nicely switchable using symbol acid and base that are actually switching the biosensor on and off. So what can we use this for? Definitely pH is not really interesting, but one of the key applications is actually antibiotic monitoring. And for example, antibiotic monitoring is crucial for monitoring the rejection of specific antibiotics, or also monitoring dependence on specific antibiotics, and also the widespread of rejection to specific antibiotics in the body. So what we did actually, we used a specific opening of beta-lactamates, which is a specific molecule that is typical of penicillin. And we looked at the beta-lactamase opening in terms of pH change. So we used the change on pH to actually monitoring the concentration of penicillin in specific analytes in this case, achieving on a wearable device a limit of detection of 50 micromolar, which is essentially within the range of clinical relevance in this case. So one of the key applications that we are now targeting is actually focusing specifically on devices that could focus on bioelectronics. Of course, now I can't promise that that device is going to be definitely integrated on the body, but looking at Christmas 2027, for example, we are now in a new project, which is a European project called Neurofibers, and we're looking at transferring from textiles into actually living electrodes. So trying to integrate graphene-based electrodes in, for example, living scaffolds where cells can proliferate within the device and incorporate the device itself, provided, of course, the device is biocompatible. And at the moment, we have some preliminary results here. You can actually see graphene electrodes that are directly integrated into these blood vessels. And actually, the graphene electrodes are spontaneously helping regenerating the tissues at this moment. Of course, I hope to give you more results roughly in 5 years' time, because that's roughly the time of this project. However, we are now shifting from textile-based biosensing devices in actually bioelectronic devices using graphene and two-dimensional materials. And with this, I want to thank everyone, and particularly my funding. So the UKRI funding, Imperial College, EPSRC, the Graphene Flagship, and also Trinity College in Cambridge, and the ERC, as well as Isaac Newton Trust at Schlumberger, and all my collaborators at Imperial College, the University of Cambridge, Trinity College Dublin, Jiangnan University, Nanjing University, and the Politecnico of Torino and Milan. And of course, I would like to thank you for your attention and listening. Thank you very much.
Thank you very much, Professor TORRISI. The floor is open for questions.
Okay, very nice talk. I have a question is about, you give some examples for the pH testing, right? Yeah, as a sensor, did you test any other parameters? Yeah, how about the result? You know, because if you want use for this biodetector with that, you must think about not only pH.
Yeah, absolutely. You're perfectly right. Of course, for limitation of time, I didn't expand the entire characterization. So what we looked at also is, for example, monitoring of specific ions. So we looked at potassium ions and sodium ions. These are crucial, of course, for the I would say biochemical or chemoresistive sensors or biochemical sensors, but also they're very important for water purifications. So the idea of using textile or I would say fabric-based devices has a double application, at least in what we see at the moment. One is bio, but the other one is also in water pollution monitoring with specific application to heavy ions. Yeah, so you're perfectly right. And at the moment, we are also expanding, we're moving towards enzyme-based sensitivity. So we're trying to use enzyme incorporated in specific, for example, specific polymers or specific hydrogels, so that you can actually have selectivity coming directly from the enzymes. Of course, the difficulty is having the enzyme per se being stable in specific polymers or specific hydrogels, but we're working on that at the moment because textile absorbs a lot of water. So when you put the hydrogel on top of textiles, that becomes a bit of an issue.
Okay, great. Okay, others?
So you have shown that when you are bending the printed devices and they still behave as transistors. So
correct.
But on the other hand, we can see that after washing and after bending, their output characteristics has changed a little bit. So when we are using these things as sensors, how do we discern whether it's because the textile has been either worn out or bent, or we're actually sensing something such as pH value change?
That's a very, very good question. Yeah, so the two measurements are different. So in this case, we are looking at the IV curve. So you're perfectly right. There is a drop in current as a function of the bending or the washing cycles. However, the mobility, which is depending on the derivative of this curve, actually is relatively constant. So essentially, we have a mobility that doesn't change too much as a function of the washing cycles. And also, this device is not going to be, the device per se is not going to be used as a washing device or wearable device and biosensing device at the same time. So you have your device, which is for biosensing, and that's a one-off device. So it's a disposable element. So you use it and then you dispose it off. That would be one type of application. In this case, instead, I'm showing field effect transistors for, as I showed you earlier on, for integrated circuit applications. And in this case, the constant mobility is what you need when you want to have, for example, complementary logic or specific NMOS or PMOS logic. So the two applications are using the same materials, but they are not going to be happening at the same time. So the biosensing device, the way we see it, is a disposable element. So you open, you use it, and then you dispose it off.
Okay, thanks.
Would you provide, thanks for your nice talk. So would you provide your opinion on the biocompatibility or the health issues with these 2D materials? Because you are using it for biosensing, and this has been an issue for years now.
Absolutely.
So yeah.
Absolutely, that's a very good question. It doesn't have a complete answer yet. So I mean, there is and I know, for example, the European Union side, because I was involved in this graphene flagship. In particular, there is a specific work package looking at the biocompatibility of graphene, and I'm sure that other countries and other continents are definitely looking at this as well. So this is also preventing the widespread use of graphene in industry. So for graphene, more recently, I would say, unfortunately, but thanks to the pandemic, there has been actually a huge investigation on graphene specifically for biochemical and biosensing application. And actually, there are 3 key papers showing that under specific morphological shapes of the graphene, so specific diameter of the flake size, specific thickness, a specific concentration of functional groups, you can actually consider graphene as biocompatible, because this material essentially doesn't degrade over time within a cell, and also it doesn't affect the cell survival. So cytotoxic compatibility essentially has demonstrated that. However, there is an entire big question open on the other 2D materials. And actually, this is still a research that is ongoing. I know, for example, from the graphene flagship side, there are 3 groups that are heavily investigated this. There is a group at CNRS in Strasbourg. There's a group in Trieste, Professor Maurizio Prato, and then there is a group in Strasbourg, also Professor Paolo Samori is also investigating that, for example. So, but I mean, there isn't really a conclusive answer to that. And I know it also very well, because the European project I was talking about is trying to incorporate these devices into the body. So you can imagine how difficult it was to get this project accepted to reviewers when you want to convince them about that. So yes, yeah, it's an ongoing project, it's an ongoing answer that we're trying to find.
Okay, very helpful. Thank you.
Thank you so much. Unfortunately, we have to move on due to time constraints. Let's thank the speaker again, and we are going to have next Professor Lauren Marbella from Columbia University. Professor Marbella, are you online?
Yes, yeah.
Okay, yeah, the floor is yours.
Okay. Just 1 minute. Okay, thank you so much. So the systems that I'm going to tell you about today are anode-free batteries. So whenever I say anode-free, I don't necessarily mean literally that the batteries don't have anodes. What I mean is that from a traditional lithium-ion battery, what we're going to do is take out the graphite anode and just leave behind the bare copper current collector. In this system, we're going to have all of the lithium inventory stored on the cathode side of the battery. And then during the first charge, the lithium is going to leave the cathode, and we're going to deposit a lithium metal anode in situ. That lithium metal will be deposited on that copper current collector. We like anode-free batteries because they allow us to improve the energy density of the cells. And what that translates to is cheaper batteries that allow us to get much greater range for electric vehicles. And they're one of the few technologies that can allow us to possibly electrify aviation. The one issue with anode-free batteries is that just by nature, they have to use a lithium metal anode. And lithium metal is one of the most reactive elements on the periodic table. So as soon as we start to plate that lithium metal onto our copper current collector, the lithium metal is going to start to react with our liquid electrolyte. our liquid electrolyte is going to start to reduce and decompose, and those decomposition products are going to deposit on the surface of our lithium metal. That reduction process is going to consume some of the lithium from the electrolyte salt. So we're going to have a loss in our Coulombic efficiency in the battery just to the formation of this solid electrolyte interphase layer or the SEI layer in the battery. If we have a lot of heterogeneity in this SEI layer, we're also going to have uneven current distribution across our lithium metal surface during the plating step. What that's going to lead to is the formation of current hotspots that can allow lithium filament growth during that plating step, like I'm showing here. During the subsequent stripping step, these filaments can start to strip at the root, and we can actually have lithium metal detach from the underlying electrode, and this is what's known as dead lithium. Dead lithium is electrochemically inactive, so these lithium chunks can no longer participate in the reversible electrochemistry in the cell, and this leads again to lower Coulombic efficiency. There's been a lot of efforts in terms of electrolyte engineering to improve Coulombic efficiency values and lead to much more reversible plating and stripping in lithium metal batteries. So what this does is it changes the solid electrolyte interface that forms during that first plating step, and it forms these bud-like architectures on the surface that are much more reversible. And again, this leads to higher Coulombic efficiency. But whenever we have those anode-free cells, of course, what we have to take into consideration is our cathode selection, since that's where all of our lithium inventory is initially stored in the cell. So if we choose something like an NMC cathode, which I'm showing here on the left, these materials operate at a much higher voltage than something like LFP, which is shown here on the right. So NMC is used in high energy batteries, whereas LFP is used in fast charging batteries. Because these are operating at a higher voltage, they're much more susceptible to electrolyte oxidation reactions, and these materials also suffer from oxygen evolution during battery cycling. These decomposition products from the cathode side of the battery can cross over to the anode side where they're deposited into that SEI layer, and again can change lithium deposition morphologies. Both of these materials are also susceptible to transition metal dissolution, and because they have different compositions, we will get different transition metals that are also incorporated into our SEI layer. So ideally, what we want to be able to do is understand how lithium deposition, dead lithium, and SEI growth is impacted by our choice of cathode. One of the most powerful techniques that we can use in order to study these individual processes and how they're coupled to one another is NMR spectroscopy. So what I'm showing you here is one of the most simple NMR experiments that we can run. This is just a one-dimensional lithium-7 NMR experiment. And what you'll see is that we get excellent chemical resolution between our electrolyte and any SEI that's formed in the system. So this shows up in our low frequency region around 0 ppm. And our lithium metal electrodes that show up in our high frequency region around 270 ppm. If we zoom into this high frequency region, during cycling, we can also get resolution between our underlying bulk electrode, which shows up around 247 ppm, and any filaments that are actually growing off of the surface here, which show up around 270 ppm. So again, this is a great tool to measure all three of these processes as a function of our cathode choice. But what I'm showing you here on the left is just a cartoon of a battery. This isn't what a commercial cell actually looks like inside. If we take a look at a commercial battery that's actually used in a real application, what you'll see is that there's multiple layers of anode and cathode that are stacked together. And this is to actually achieve the energy densities that are needed in real applications like electric vehicles. The way that these layers are arranged depends on the actual manufacturer. So some manufacturers use this single sheet stacking, And this may impact cell failure in anode-free batteries. So here we have alternating layers of anode and cathode, but you'll notice that on the sides here, the separator doesn't actually protect these two layers from one another. So whenever we start to have lithium metal deposition, we can actually have lithium creep across here and short circuit the cell during battery operation. If we have a cell from a manufacturer that uses prismatic winding, you can see that the two layers are much better protected from one another. So these cells aren't as susceptible to short circuiting events, but they do suffer from more internal stress, where the lithium deposition in these flat regions will likely be different than those in these bent regions here. So ideally, what we want to be able to do is perform our NMR experiments in cells that are representative of these multi-layer architectures. But if you've ever gone for an MRI, you know that the first thing that they ask you to do is to take off all of your metal jewelry. So whenever we were first starting out these experiments, we weren't sure if they were going to work, because what these measurements force us to do is put a lot more metal in terms of our current collectors inside of the instrument. So the way that we actually approached this measurement was we took our multi-layer pouch cells, we removed this external casing, and we took out the multi-layers. We cut them so that they actually fit inside of our operando NMR cell, and we rewound them into this prismatically wound architecture so that they were representative of the original commercial cell. We went ahead and we performed an operando lithium-7 NMR experiment on this multi-layer cell. So what you're looking at is the data that we got from an NMC copper, so an anode-free battery that was extracted from a 200 milliamp hour pouch cell. This is a 30 milliamp hour in situ cell, and it's cycled at a current of 10 milliamps. So this corresponds to a rate of C/3. All that means is that each charge and discharge cycle takes 3 hours. And this measurement gives us a time resolution of 8 minutes. So let's walk through this data step by step. So what I'm showing you here is a breakdown of each charge and discharge step. So the orange spectra here show our lithium metal signal at the end of plating. The purple signal shows us the lithium metal signal at the end of stripping. So we're first going to focus on the lithium metal signal that's formed at the end of plating to evaluate our lithium morphology. And we're going to add in this dotted line to guide your eye. So if we just look at the lithium metal signal that's formed after the first charge step, so the first plating, what you'll notice is that signal shows up at lower frequency with respect to all subsequent cycles. It's also relatively symmetric. This tells us that these deposits are likely relatively smooth compared to subsequent cycles. We can take this cell apart and look at it with SEM, and that's exactly what we see. So we have these bud-like architectures. If we take a look at the spectra that we get at the 10th charge cycle, you'll see that we've started to grow this high frequency shoulder here. And this corresponds to what we see in the SEM of this cell, where we started to grow these lithium filaments. So what we can take away here is that the lithium deposits formed from our NMC cathodes, so those high energy density cathodes, increase in surface area as a function of cycle number. So what we did next was we went ahead and we compared to the lithium deposits that were formed from LFP. Again, if we focus on the spectra shown in orange, so the lithium metal deposits formed at plating, you'll see immediately that the spectra are much more complex. So we have some regions at low frequencies, some regions at high frequency, and this would suggest to us that we have a lot of different morphologies formed from our LFP or our fast charging cathodes. Whenever we take a look at these cells after disassembly in the SEM, again, that's exactly what we see, where we see some of these bud-like morphologies. We also see some fluffy needle-like deposits, and then we also see some of these high surface area lithium filaments. So takeaway here is that lithium plating from LFP cathodes is very heterogeneous, and that's also representative of what we see in our operando NMR experiment. So the next thing that we wanted to do is evaluate, based on these lithium deposition morphologies, where are our sources of lithium loss in the system? We can first look at the differences in Coulombic efficiency from the electrochemistry. So the NMC cells show a Coulombic efficiency of about 84%. The LFP cells show a Coulombic efficiency of about 94%. But the one drawback here again is that the electrochemistry is completely blind to whether our lithium is being lost to dead lithium left behind on our copper current collector or SEI formation during electrochemical cycling. So we go back to our NMR experiment and we look at our lithium metal region. So this is the data from our NMC cell. And what we see whenever we compare the stripping and the plating in this region is that we have a lot of lithium left behind on our current collector during the stripping step. So if we look at this pictorially, we see that we have a lot of dead lithium accumulation that's contributing to this low Coulombic efficiency value in our NMC cell. On the other hand, for our LFP cell, while we see that we have a little bit of dead lithium accumulation in the first cycle, after that first cycle, our stripping and our plating is relatively reversible in comparison to one another. So again, what this tells us is that we have a little bit of dead lithium formation on our copper current collector, but then that's pretty much all we have. And our quantitative values also reflect that. In order to understand how much SEI formation accumulates in these cells, we can just move down the spectra to the low frequency region and quantify how much surface reactions occur over the course of electrochemical cycling. So in both cases, we do see the accumulation of lithium on the surface of these particles, and we can also quantify those values. So here we've tabulated those values and shown the relative ratios. So in the NMC cells, 93% of our lithium loss is coming from dead lithium in comparison to 82% in our LFP cells. And the lithium that goes to the SEI in our NMC cells is only about 7%, whereas it's about 18% in our LFP cells. So we have a higher percentage of lithium loss to SEI in the LFP in comparison to the NMC. So using this tool, what we can do now is study the impact of actually changing our electrode surfaces, electrolyte engineering, and stacking architectures to know precisely how these changes in battery chemistry are impacting lithium loss and further engineer and tweak these chemistries to optimize battery performance. So just to wrap up, I'd like to thank the various funding sources that have supported this work and the students that have worked very hard on this project, and I'd be happy to take any questions.
Thank you very much. The floor is open for questions.
Max, see you open. Oh, not yet.
Max, are you still connected? I'm sorry, I could not hear you.
Okay.
Maybe I can go ahead and ask one question while we are waiting for Max to join. So it's my understanding that your NMR is offering in situ operando measurement for high precision of chemistry, lithium chemistry, but it is not operated in correlation or with a in situ SEM, right? I just wanted to clarify. So you have achieved high chemical resolution, and you are using SEM as a morphology correlation to the observed NMR data.
So the you're right that the SEM is done ex situ, but we get morphology information from the NMR. This was just to confirm that we were right in the NMR assignment. So the fact that we have this shoulder here, and it's a little bit hard to see in this zoomed out, but let's go back here. So you can see in this spectrum here, this here corresponds to our flat electrode. This here corresponds to lithium filaments growing off of the surface. And the reason that we're able to distinguish these morphologies here is because of an orientation dependent effect in the NMR. So in these experiments, we're very careful about how we place the battery in the magnet. So lithium metal that's oriented perpendicular to our external field gives this frequency shift at 247. So that's where our bulk electrode is. And then lithium metal that's oriented parallel to the field, so filaments growing off of the surface, give a higher frequency shift at 270 ppm. So we are indeed getting morphology information from the NMR as well.
Thank you.
So can you go down 2 slides? Just move forward 2 slides. Yeah, that, right. So on the main figure to the right, on each curve, can you help remind me what's the y-axis?
Yes. So here is our cell voltage. So this just represents charge and discharge of the battery. So this is lithium being deposited, and then lithium being stripped off of our current collector. And then the y-axis here is chemical shift. So this tells us about the chemical state that lithium is in. So in this region, we're going to see our electrolyte and our SEI. And then in this region, we're going to see lithium metal, and we're going to see changes in our lithium metal morphology because of the orientation effect that I just talked about.
Yeah, I was asking about the vertical axis on the right.
Oh, I'm sorry.
The vertical axis represent, because it doesn't appear to be labeled.
Oh, this here is,
right.
This also just corresponds to time. So here, since it's an operando experiment, it's also corresponding to this axis here in the electrochemistry. So we can also think about this in terms of capacity. So what we see is lithium being plated as a function of time. So here we're charging the battery, moving lithium atoms from the cathode to the copper current collector. And time here is going to, the time that this takes is going to be 3 hours for a full charge cycle. And then time to discharge is going to be, so this is a faster cycle than I have labeled up here. So this looks like somewhere around 2.5 hours about, and another 2.5 hours because it's a little bit less than 5 cycles. But it's just time to plate, time to strip, time to plate, time to strip. Yeah.
Okay, thanks.
Okay, I can go next. So you showed your work on lithium batteries. So I was wondering if you change your systems to like a sodium batteries, would the technique be the same, or do you have to change some variables?
Yep, we could do the exact same experiments with sodium. We would just change the nucleus that we're looking at to be sodium, and we could do exactly the same. Yep.
Okay, so it's a powerful.
It's actually a very good nucleus to look at as well. Yeah.
Okay.
Wonderful. Thank you very much. For the interest of time, maybe we should move on. And thank you, Lauren, for your presentation. We have last speaker of today's session, Professor Dong Renhao from Technical University of Dresden.
Hello, I'm here.
Yes.
Yeah.
Yes.
Now I'm
would you
sharing my
please
screen.
put your presentation into
Yeah.
full screen? So
Yeah, full
we'll
screen.
be able to see. Okay, excellent. Thank you very much.
Hope you can see it. Okay, yes. Okay, thank you for your kind introduction, dear panel committee and dear audience online. My name is Renhao, and many thanks for providing me this precious chance to share our recent work on interfacial synthesis of organic 2D materials. So organic 2D materials refer to crystalline 2D nanostructures comprising carbon-rich repeated units linked by covalent or non-covalent bonds. Representative organic 2D materials include single layer or few layer 2D polymers, layer stacked 2D covalent organic frameworks, layer stacked 2D metal organic frameworks, and their van der Waals heat structures. And besides the unique features of these organic 2D materials, such as abundant ligands and linkages, high crystallinity, and well-defined polar structures, recent advances have discovered many interesting physical and chemical properties in these organic 2D materials. For example, they present the high activity for photoelectrocatalysis and energy storage. Due to the intrinsic electronic properties and magnetic properties, the organic 2D materials can be further utilized as active layers for optoelectronics, spintronics, sensors, superconductors, and information technology. So due to these interesting physical and chemical properties, the organic 2D materials have attracted increasing attention. However, there are still many fundamental key questions for the development of organic 2D materials. Technically, one question refers to how to develop the novel synthetic and chemical methodologies toward the precision synthesis of organic 2D materials, and how to tune the topological networks and control the morphology, the size, and the defects. So another key question refers to how to precisely elucidate the structure and properties of organic 2D materials. For example, how to figure out the reactive size, the edge structures, and the defects, and how to explore the most interesting properties and the killer applications. To address the above key questions, I proposed to combine the 2D polymerization chemistry and the interfacial chemistry for the synthesis of precise organic 2D materials. So by developing multiple synthetic methodologies, we aim to achieve the single crystals or single layer or few layer organic 2D materials. So the special focus is to establish multi-component heterostructures based on the developed organic 2D crystals, aiming for the unpredicted superlattice and extonic physical and chemical properties. So with these synthetic 2D materials, we further go into device integration and function research. So next, please allow me to briefly introduce several contributions to the organic 2D materials from our group. So the first contribution is to develop the chemical methodologies of 2D polymers and 2D comps. So one strategy for the 2D polymerization relies on the dynamic covalent chemistry that enables the self-correction on the formation for high crystallinity. For example, the Schiff-Base reaction, the Born-Lise reaction, and the coordination reaction. The second strategy relies on the monomer pre-oxidation before the bond formation. So usually the irreversible reactions can be involved in this strategy, such as Wurman coupling, Suzuki coupling, and glass coupling. So based on the two strategies, we are able to construct highly crystalline or even single crystalline 2D polymers or 2D comps, such as 2D polyimine, 2D polyimide, 2D polyester, and pyrazine-linked semiconductive 2D comps. In addition, in close collaboration with Professor with the Kessler group, we are able to evaluate the local structures such as the boundaries and the defects at the near atomic resolution level. So our works just presents the sit-out structure characterization, and it's helpful for us to establish a reliable structure synthesis property relationship. So the second contribution is to develop the 2D conjugated morphs for morphotronics. The 2D conjugated morphs refer to a class of layer stacked morphs with strong in-plane conjugation and weak out-plane one-to-one interaction. So in our preliminary work, we have designed and synthesized a series of conjugated building blocks. For example, the benzene-based, tryptophan-based, disulfide-based, and coronium-based ligands modified by the cell, amino, and hydrogen oxide groups. After linking with the transition metals, we were able to achieve layer stacked morphs, and we discovered that these conjugated morphs can exhibit intrinsic electrical conductivities due to the strong pi-d conjugation. And they can present high conductivity and high mobility. More interesting, their band gaps can be engineered from metal to semiconductor. And even some 2D conjugated morph modulators have been theoretically predicted as the new generation of organic topological insulator. So here's one typical example from our side. The iron coronium-based 2D conjugated morph can act as a kind of ferromagnetic semiconductor with high conductivity and a narrowed band gap. And recently, we also shipped the research concept named as morphotronics, which expects to provide a class of complementary morphoelectrode materials for the optoelectronics. We expect it can overcome some limits existing in the dominated silicon electronics and organic electronics. And the third contribution is to develop interface assisted synthesis methodologies. So in fact, the interfaces have been utilized for the controlled synthesis of various inorganic 2D materials. These interfaces include the air-water interface, liquid-liquid interface, gas-solid interface, surfactant bilayer interface, and the solid surface. Particularly, we would like to contribute to develop the wide interfacial synthesis that can allow us to synthesize large area, freestanding crystalline film with controlled thickness. Next, I would like to briefly introduce you 3 representative interfacial synthesis strategies developed by our group. The first example from our side is to synthesize polycrystalline trifluidine-based 2D morph modulator by the Langmuir project method at the air-water interface. This cartoon just shows the synthetic procedure. Firstly, the solution of THT ligand was supplied on the water surface in the LB trough. Then we inject the nickel salts in the sub-water phase. So with the diffusion of the metal salts onto the water surface, the 2D coloration polymerization can be triggered on the surface. And after the polymerization, we can see the formation of 2D morph modulator. And then we can easily transfer the 2D morph film from water surface to different kinds of substrates for further characterization and device integration. The optical image and the AF measurement demonstrated a centimeter-sized modular 2D conjugated morph film. And we also extended this LB method to different kinds of 2D morph systems. In our recent work, we utilized the LB-assisted interfacial synthesis method to synthesize another kind of 2D polyimide modulator. Then we further transferred the 2D polymer modulator from the water surface to the graphene substrate and constructed the 2D polymer graphene one-to-one structures. And this case structure exhibited ultra-fast interlayer charge transfer that is even superior to the traditional graphene MS2 one-to-one structure. So this work just provides us an efficient strategy to prepare one-to-one structures with a large area in the centimeter size that can be also extended to different functional 2D polymer systems. The second strategy is to employ the liquid-liquid interface to to synthesize the multi-layer 2D morph film. So here, a water and chloroform biphase system was constructed where the monomer and the salts can be dissolved in the two phase separately. So with the diffusion of the monomer and the salts to the interface, the polymerization was triggered at the interface, and then we can achieve centimeter-sized morph film. And the film thickness can be tuned from 20 nanometer to 2 micrometer by controlling the reaction time and the monomer concentration. Next, we employed the terahertz spectroscopy to study the photoconductivity property in this morph film. The terahertz results just suggest the pure the response and demonstrating the band-like transport in this film. So combined with the DFT calculated effective mass values and also the scattering time achieved from the terahertz measurement, we can calculate the mobility, and the mobility can even reach as high as around 220 square centimeter per voltage second. So this work just highlighted the high mobility semiconductor in 2D conjugated morphs is very promising as active layers for photoelectronics. So now I briefly introduce the third interfacial synthesis method. So recently we developed a spectrum monolayer assisted interfacial synthesis, named as SMICE. So in this method, spectrum monolayer on water surface was utilized to induce the pre-organization of the monomers and the spectrum. And then the subsequent polymerization can lead to the highly crystalline 2D polymer film with large size domains and tunable thickness. So here I would like to take the synthetic 2D polyimide as an example to show some more synthetic details. So firstly, we spread the ionic surfactant on the water surface to get the surfactant monolayer. Then we inject the charged porphyrin ligand into the water solution. So due to the electronic interaction between the ligand and the surfactant, the porphyrin ligand can pre-organize under the surfactant surface to get the long-range ordered network. Then we inject the second monomer into the water solution. Due to the diffusion of the monomer onto the water surface, the co-polymerization can be triggered at the water surface. And you can see the side product is water. It is taken out from the ligands, and then the polymerization can be successful. And to achieve the heavy crystalline 2D polymer film under the selected monolayer. So here is the characterization about the obtained 2D polyimide film. This film just shows the thickness around 2 nanometer, indicating around 5 layer stacked film. So the electronic diffraction pattern also reveals the square unit cell with the size of 3 nanometer and A stacking model. Then we visualized the molecular structure of the 2D polyimide by the aberration corrected high resolution TEM. So which also showed the square lattice with the 3 nanometer spacing. And the average single crystalline domain size can reach as large as 3.5 square micrometer. And in our newest work, we also demonstrate that the formation of a charged 2D polymer based on the Karpinski reaction by the SMICE method. So the Karpinski reaction is a well-known irreversible reaction for the synthesis of a charged linear polymer. So usually it includes 2 steps, the ring opening step and the ring closure step. However, in our work, we can manipulate the pH values in different reaction steps to promote the reopening and the ring closure. Thus, we can enhance the overall reaction kinetics. So as a result, we can achieve the highly crystalline 2D polymer even with the single crystal domain size over 100 square micrometer. Here, I would like to take the concentration condensation between the amino substitute porphyrin monomer and the triphenyl as an example to show what we have achieved. So based on the interfacial irreversible characteristic reaction, we can achieve single crystalline 2D polymer nanosheets, and the single crystalline domain can reach over 120 square micrometer. And the thickness of the nanosheets can be tuned from 2 nanometer to 20 nanometer with the reaction time and the monomer concentration. We also defined the crystalline structures with the square lattice by the atomic resolution TM imaging. And we clearly see the porphyrin monomers and the triphil ligands in the 2D network. And due to the high density positively charged size and the highly ordered highly ordered POSI-1D channels, so we also applied this resultant charged to the polymer single crystals for the osmotic energy conversion. So with the potassium chloride as the electrolyte, this charged to the polymer exhibits very excellent ionic selectivity and high power density. And then even this system can be comparable, the performance can be comparable to the traditional graphene and other inorganic 2D materials films. So this work just provides us a new strategy to construct the large-sized 2D polymer single crystals based on the interfacial irreversible reaction and extend the application of 2D polymers for energy storage and conversion. So to be summarized, so we are developing the interface-assisted synthesis methods for the construction of organic 2D materials, including the conducting 2D conjugate morphs and the 2D polymers and the 2D cords. So our preliminary work demonstrated that this interfacial synthesis strategy is very reliable and very efficient. But however, there are still many open questions for this research field for us to fight there. So in the last but most important slide, I would like to appreciate the great help from my colleagues in TU Dresden and my close collaboration with many collaboration partners, and also appreciate the hard working from my group members. And also appreciate the great support from Humboldt, ERC, and DFG fundings. Then thanks for your attention. I'm open for any questions and comments. Thank you very much.
Thank you very much for Professor Dong. The floor is open for questions and answering session.
Maybe I go first for general questions. Actually, a lot of researchers on 2D materials. Okay, yeah. So Renhao, you're working on these 2D materials. So, can you give some perspective for the real application or killer application for these, super materials?
Yes, that's a really important question for us. So we are also fighting for this for many years. From our previous work, of course, we firstly focused on the electronic properties. We would like to extend the 1D polymer from the conducting polymer from 1D to 2D. So we expect to utilize this new conducting 2D polymer for the electronics, for example, the FET. Yeah. But you can see that for the 2D polymers, we also have very defined polar structures. It means that we can even utilize it for the ionic transport. That means that we can combine the ionic transport and the charge transport in one device. Then it provides us to utilize this organic 2D material for the OECT device. Okay, this is, I think, this is the future direction. And of course, another direction is for the sensors. I think just several speakers also mentioned the different chemical sensings and biosensors. Okay, because for our materials, it's intrinsic conducting materials and also with abundant active size and also defined polar structures. It means that we can design different molecules for different sensors. And for example, utilize for the vapor and utilize for the protein, even also the virus sensings. I think based on the electronic properties, the conducting organic 2D materials should have very wide application there. Of course, another direction should be utilized based on the polar structures for the separation. Yeah. But I did not mention this in my presentation, so we are still fighting on this direction. Maybe I can share more information in the future with you. Okay.
Thank you.
I can go next. Yes. So actually, Alice stored my question, so I have to change my question about the application. Yes. So I was wondering about the thermal stability of the polymer-based devices. I'm also working on polymer-based devices, but the weak point is always the narrow range of the thermal stability. So, would you provide your opinion about that?
Yes, indeed, I also mentioned this advantages of this highly crystalline organic 2D materials. For example, for the 2D morph materials, and the thermal stability is, I think, is not bad. So Yuerui, it can be still stable till 400 to 500 Kelvin. It means that it has very good thermal stability. But for the 2D covalent polymers, I also mentioned that maybe it can overcome some limits about the low thermal stability of the traditional linear polymers. Also, that's due to the highly crystalline structures, and also due to the robust carbon-carbon bonds. So of course, how to develop the robust carbon-carbon bond-based 2D polymers now is very, very interesting, and it can enhance the thermal stability and the chemical stability. Yeah.
Okay, thank you very much.
Yeah, thanks.
Thank you. So maybe I can jump in and ask one question. You mentioned about your vision of a morph as a platform for electronics. I'm wondering what kind of interface is typically between metal and morph structure. Are they of I should say ohmic junction, or are they Schottky barrier based, or what would determine the interface between metal and morph structure?
You mean the metal and the morph in the structure? You mean the metal as the electrode or as substrate?
Yeah, metal as an electrode, because you are going to have some kind of contact, right? Eventually.
Okay, I see. Yeah, so here, of course, we first would like to utilize the conductive morph as electrode materials. But if we would like to discover the intrinsic transport properties, we have to do some contacting. Yeah, for example, we utilize the silver or copper or even the carbon paste to contact on the morph film. I think for the moment, there's still not too many detailed answers about this interaction. Yeah, so for the moment, the people still would like to develop the band cap engineer the morph materials. But how to integrate the morph into the real device, I think there's still quite a long way to go. I think for your questions, for the moment, I don't have a very solid answer about this. Yeah.
Okay, thank you.
Yeah.
It seems like we are running out of time, and we probably have to hold up all the rest discussion offline. With that, I would like to take the opportunity to congratulate all of the finalists of iCANX Young Scientists, and yeah, we'll have 30 minutes. Oh, I'm sorry.
No. We will start our ceremony and 20. What time now?
10:30. Yeah. So we have 10:30 as our ceremony time.
Yeah.
So
there between we'll have a short video for what happened on iCANX and 2022. Yeah, please enjoy. Okay. Yeah.
不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱，我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can。没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can。能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌，不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱，我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can。没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can。 不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can，能够像我一样飞越最高山岗。I can, I can， 没有什么可以阻挡心中无限的力量。不再是奇迹，不再是幻想，此刻真感觉全世界为我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。I can, I can，没有什么可以阻挡心中无限的力量。I can, I can， 你也能够像我一样飞越最高山岗。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞，不再为曾经失败放弃或感伤，努力才是真的方向。I can, I can， 没有什么可以阻挡心中无限的力量。I can, 不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。I can。没有什么可以阻挡心中无限的力量。I can， 你也能够像我一样飞越最高山岗。创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经失败放弃或感伤，努力才是真的方向。I can， 没有什么可以阻挡心中无限的力量。I can。像我一样飞越最高山岗。I can， 没有什么可以阻挡心中无限的力量。不再是奇迹，不再是幻想，此刻真感觉全世界对我鼓掌。不必太在意身旁惊奇的目光，可以点点头，可以放声歌唱。我创造奇迹，我拥有梦想，我希望看见所有骄傲的脸庞。不再为曾经。
It's like really okay, exciting moment. So don't worry, we have a lot of things to do. Okay, yeah. First, let me first. I think almost everyone here, right? Yeah. So, not everyone here. So if someone, the winner not here, I will, just flow down to the next. Yeah. So that's our schedule. Before we got to the final result, let me first, to give you a brief summary of what we did in 2020, and also what we're going to do in 2023, because this will have a invitation to all of you, and I hope everyone can hear me clearly. Hello everyone. This is Alice. I'm so glad today to represent for the committees to do this award ceremony. So this was scheduled for our 2022. I think last year at this time announced this was very exciting, but the time really fly, right? Yeah. So and this year we have so many wonderful speakers on this stage. We see all this lovely face, and we remember all of their nice talks and our young scientists and almost everyone from everywhere. We also have a summit in spring. though it was a kind of a story because it really takes several times to do it. It's on-site or it's online, but eventually we make it. Yeah, we made online. We got a lot of speakers here. And it's really amazing here. You know, we have this 100th anniversary. It's unbelievable. And the very beginning, 2020, during COVID-19, I just want to do something, you know, make it meaningful, but never know we can continue for 100 weeks. I think me so can feel that, and Nick, you know, also can feel that it's like a dream come true. First, you know, several weeks, we really struggled how to find the speakers, right? With how to run it. But now you see, you know, full of the very nice speakers and, you know, 100, you know, and, you know, weeks. That time I really moved. So we continually this year to have so many nice speakers and so many great talks from different places. And we even have some, you know, new things to show with everyone, not only, you know, this several weeks, you know, everyone competing for this Young Scientist Award. And we also have these new things. We have our iCANX club in Beijing. This was a very nice place. Yeah, you see that this was the exhibition hall. Looks like space. Yeah, we try make it like meta, you know, yeah, to make something really fun. This was some place for chatting, for group meetings, you know, even for the talks, even have a very nice outdoor space, you know, can enjoy beers, talks, can enjoy all these parties. That's what started in August. Yeah, so as continually for several months, so we are very happy with this. This was the 4 speakers on this list. We're so proud of you. We try our best to get everyone's head on it. Okay, now you should be proud of you already on it. Yeah, so this was, you know, for before we come to the award ceremony, I know everyone was there really kind of a stress. So try to release a little bit of stress, tell you what are we going to do next year. Yeah, so and 2023, I'm so proud that we designed these very nice pictures because we have a dream is try to get the science go around the world. It really become a common language for everyone, become a, you know, a real place, enjoyable, you know, event for everyone to get on stage to be connected, you know. So next year we're going to have 100 countries, 1,000 scientists, and many peoples. Yeah, so yeah, so that's a really a big picture. So going to have this now, we start to have one very important, you know, special issue as for the youth talks. And every Tuesday we keep iCANX, and Friday we will have a one, you know, special channel for the young scientists, and every Tuesday. So this was our dream because in 2023 we think it's time, you know, to move forward to get a big picture. So and this youth talk we're going to, you know, sorry, yeah. We lost some message. Oh, so okay. What's wrong with this? Got some. Okay, here. So every Tuesday we're going to have these youth talks. We try to, you know, have it hybrid, half in Chinese and half in English. So the half in English will be organized by the global young scientists here, like all of you. So the plan is each Friday, you know, we have 2 hours. We focus on one topic, you know, 9 minutes talk, and we can plus another 30 minutes for panel discussion. What we want to do is we really want to invite the world leaders in youth, so to join. So you need to invite the speakers from different countries and regions, not just from your place. Okay, that's the only, you know, requirement for this youth talks. So please think about that. For the Chinese version, we already form a team. So all these people that will help to, you know, organize the Chinese version. Yeah, every another week we'll have this English one. So now we're going to, you know, want to have all of you to join us this 24 weeks, and we'll have 24 topics. We need 24 youth leaders. So I hope all of you here can take the call, right? Yeah, can answer the call to join us. If you are interested, just let me know. Send an email to this info iCANX. That's okay. Yeah, every week we'll have one special topic. Just try to invite more speakers from different part of the world to join that. Yeah, so that's this was talks for next year. So that's almost done. The pictures for we are going to have. So next year we already have so many big names will get on the stage on the Friday's talks. So as usual, every Friday we'll have a lot of fun. And so this was from iCANX 2022-23. So we're going to have 100 wearable, 100 countries, regions, 1,000 scientists, and 100 million audience. Okay, counting on all of you. So before I give you the award, now I give you an invitation. You join me, right? Yeah, no matter you win the award or not, but this was our invitation from iCANX to be one part of this big group and big family. We try to promote young scientists as as much as we can. So after all of this, let me tell you all this stories about what do we want. Let me share another. Okay. Is everyone okay? Okay, here. This is our award ceremony for this year. I hope you can see clearly and you listen clearly. Okay, once I read your name, yeah, just let me know you're here. Okay, if you're not here, I will change another one. Okay. So this was committee chairs by Paul and me. But today Paul was online, but he's in Africa. It's internet is very bad, so he couldn't speak loudly and showed up. So, but he is there. Now I speak for him and invite all of you. I'm proud of all of you. And this was our committee members. I think in last, Paul, you showed up. So so great. Yeah. Okay. Great to see your face. Okay. Yeah. We are so happy to this year we enlarge a committee. Got more support from different places, and we also got more sponsors very stable. We have ACS Nano with Applied Physics Review. We have Light, all these great partners. There are great journals like Paul Journal. Now this year is, also improving the impact factor. And this Applied Physics Review was our previous, coordinator, Professor Jagdish, was editor-in-chief. It really helped a lot to promote in physics. And sorry, where is the light? So, yeah, light is getting more important too. And one of the top journal, in this field. And this was our young scientists in 2022 applications. Everyone knows that we have a very strong applications this year. We selected 24, to be the final. We selected the 24 to join the last, final defense. Here was the pictures. And this was a lovely picture for this 24. I hope all of you here. Okay, yeah, I hope. Okay. Oh, sorry, this page was put in the wrong place. Light, the journal is our sponsor, and now is one of the top journal, not only in China, also in the world, in field of light is top 3. I'm proud of that. It's a long time, stable friendship and support. And this defense was gone for 3 days. Look, the first day we have 9, speakers. We have 5 very tough, committee members to be a jury. And next day we have, 9 too. We have another group, also 5 peoples. And today we have 6 final speakers. So we have 5, committee members here to evaluate it. come to the end. Okay, yeah, that's all of them. Yeah, the stories now come to the end. Okay, prepared. Okay, who is the first one to show up in the first week? Yeah, so so who is the winner? I will going to show them by the date. Okay, the first one is Bao Wei. Bao Wei, are you here? Hi, Wei.
Yes, I'm here.
Okay, now you got it. So congratulations, you did
Thanks,
a
Alice.
wonderful job and very good humorous stories. I think that's make a lot of sense for this talk. Okay.
Thanks.
Okay. Yeah, please answer my call, you know, to the youth talks. Okay. That's another job for you. Okay. This way, congratulations. We have another one. Jonathan, are you here, Jonathan? Okay.
Yes, I'm here. Thank you.
Okay, Jonathan, you win it. Yeah. Okay, so proud of you. Yeah, your work really like the future of the field. Yeah, please. And I hope you can organize youth talks in this field, invited all the people to join it. Right? Yeah. Okay. Yeah. So, Wei, are you here?
Yes, Alice, I'm here.
Oh,
Yeah.
okay. Shut up. Let me see you. Okay.
Yeah, I'm here.
Okay. So Wei, congratulations. Okay.
Yeah, thank you so much.
You smart fibers. Yeah. I hope you can, you know, get more smarter fibers in the future. Okay. Yeah.
Thank
great. Next one, Chen Yin. No?
Yes. Yes,
Okay.
I'm here.
Okay. Remember that. Prepare ready. Otherwise, if I call you 3 times, okay, yeah, you will go to another one. Yeah, we'll have
Thank you so much.
Yeah, so Chen, proud of you. Your new publications, very nice, very beautiful.
Oh, thank you so much. Yeah, I feel excited and humbled to receive this award. Thank you.
Okay, yeah, prepare you to talk, okay?
For sure.
Yeah. Great. Next, we're going to the second day. Yeah, so Tong Chao, are you here?
Yes. Thank you. Thank you so much.
Okay, Tong Chao, congratulations. Really great.
Thank you. It's a very huge honor for myself. Also, I would like to see all the families are so excellent, outstanding. They all deliver very good talk. I really enjoy. Thank you, Alice, and all the committee members for organizing such a
forget your
fantastic.
job. Okay. Yeah.
Thank you.
Don't forget your job. Okay.
Yeah, I hope more scientists from national lab will join this this talk, and also hope more battery scientists can join this talk as well.
Okay, great. All right, cool.
Thank you.
Who is next? Okay. Nako. Oh, Nako, are you
Hello.
here?
Hi, Alice. Thank you so much.
Okay, good.
I really
Okay, Nako,
appreciate this.
congratulations. Yeah. So proud of you. Okay, that's you'll be the very nice speaker in the last the last speaker in that day. Really great. Okay, congratulations.
Thank you so much. Thank you to the committee.
Yeah, try to get more female scientists to join. Okay, Chang Yong, are you here, Chess? Nope. Chess, you know here? Okay, Chess, we will move down. Okay. we move on another one. Okay. Okay, Aristide, are you here? No? Okay, we move to Chen Jun. Aristide, yeah, 3 times. Okay, already.
Yes.
And Chang Yong, okay, no. Jun.
Yeah, I'm here. Yeah.
Okay, okay. Yes. Congratulations, very nice talk.
Thank you, Alice, Paul, and Lick, and Miso and Zhenhui. And the audience as well. Thank you very much for your time and attention.
You can have a sleep now, okay? Go back home.
Okay.
Okay, yeah, very nice. And this is behavior SHASTRI. Are you here? Hi.
Oh, hello. Oh, hello. Can you see me okay?
I see you okay. Yeah. I hope you're not. Okay.
Thank you very much. Sorry, I'm on my phone because we just dropped our baby to the daycare. Yeah, but thank you so much. I really, I'm very thankful to the committee and also for this opportunity. So thank you so much. Yeah.
Okay. Congratulations to all of you. You did so wonderful job. Okay. That's all of the end for the for the award ceremony. And I think let me see. Okay. Sorry about this. Okay, that's it. We got this too. Don't worry about that. Okay, let's stop sharing. We have this two now here. We got instead another two here. Okay. Sorry, moved to the wrong page. Okay, I got to the the last part of that. I try to one more time ask these two guys are here. Changyong Cao, are you here? Changyong.
Hi, Alex. Yeah, I'm here.
Where are you just now? Are you sure you showed up?
Can you hear me?
Okay, I can hear you. Okay,
Oh,
need to
yes.
double check with me is a Changyong or not. Is a real person.
Okay. Thank you, Alex. Thank you
Where
for
are
the
you just
meeting
now?
and
Okay,
I'm greatly appreciate for
almost,
the opportunity.
No, Changyong, you almost missed the word. Okay, I'm serious
Okay.
on this. I announce you not here, you miss it. Yeah, now this is the last chance. I make sure you hear. Okay, yeah. Okay, we got next one. Aristide, are you here? Changyong Cao, are you here?
Oh, yes. Hi, Alex.
I know. What's wrong with that? We got some echo.
Oh, can you hear me? What?
Changyong, you mute, okay?
Okay.
Okay. Well, we got another one. Aristide, are you here? Aristide, are you here? No? Okay, I'm serious on this. Even though here you miss the last chance. Okay, so we move to the next one because we have so many nice speakers that day. On this day, we got a long line on this list. So who is the lucky one here? I hope you're here. Okay, even not here, we'll move to the next one. Okay, yeah, let's see if this one here. Jules Matthew, are you here? Jules?
Yes, I'm here.
Okay, now you are a lucky person.
Wow, that's great. Thank you.
Yeah, it is. I'm serious on this. If someone didn't hear to pick up the award, the award is gone. Okay, now you take it.
Now it's mine. Thank you so much. I appreciate it.
Okay. Very nice. Congratulations to everyone. Now please take my invitation to this 2023. Okay. Yeah, we want to have all of you on the stage and to on this youth talks. Okay. Congratulations. That's it. That's all for today. Thank you.
Thank you, everyone. Thank you.
Thank you. Thank you so much.
Thank you so
Okay.
much.
Thanks, everyone.